presented by me, Dr. Kornali and Dr. Aden right there. Sorry about the typo, please ignore it. All right, so today we will talk about a historical problem that inspired this whole research. We will talk about circular partitions, run length encoding, a little bit of formal language theory, and then our results. So, our inspiration, motivation. So there was an old story in Islamic and Arabic literature, which also happens to be in other literatures, but this is where we found ours. And it's about a ship that has 30 passengers, and they're divided into two groups. 15 are believers, 15 are not believers, and this ship was sinking. So the captain had said, like, oh, we have to sacrifice half of the passengers so the ship survives, and like it has to be like a random, we cannot be like playing favorites type. But he is very wise that he devised a plan, and one might say a linguistic strategy, using the alphabet and a verse that we will talk about a little bit later, to be able to eliminate every single non-believer, and all the believers survived. So here we go. This is, for my non-Arabic speakers, this is the Arabic alphabet. And we have dotless and dotted letters. As you can see, we do right to left in Arabic, but yeah. And this is the verse that he used. So every letter is a position on the circle right here. And we have our non-dotted letters in blue and our dotted letters in red. For this purpose, we're going to assume that our dotted letters are the non-believers that we are going to get rid of. And we count, and every ninth position is eliminated, and keep going until we have 15 out, and that way, using that verse, we get rid of all the red circles right there. So this is interesting, it's cool. So how they do it? We noticed that this has a lot of similarities to the Josephus problem. So we can see that we have like n people in a circle, here we have 30, we're using a step size 9, here we're like eliminate every k person. We're trying to eliminate 15 in here. So it's just a little bit different, but in a way it's the same. This led us to think about partition problems. So we figured that for any positive integers, nk and r, such as r is less than n, there exists a balanced partition of n into r groups using step size k, where each group has either the floor or the ceiling function of n over r elements. So, and we have two approaches for this partition problem. We have a removal approach and a non-removal approach, and I feel like the names are pretty indicative of like what they mean, but a removal approach is every case object we land on, we remove, while the non-removal approach, we just mark it or label it and put it in a group immediately. So, let's delve into that. Our non-removal approach. So basically we have, say we have 9 objects, we want to put them in 3 groups using step size k. We can see here, we will just like put the first time in red, then green, and then gray. So we go 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on, until we have 3 different groups labeled differently, and each of them have 3 objects in them. Okay, this is with the removal approach. So in here we will talk about a removal approach using dummy objects, and then we will talk about just simple, straightforward removal approach. So for 10 objects, and you want to put them in 3 different groups using step size 4, we need to add 2 dummy objects, so that 3 modulo 10, which are objects plus the 2 dummies, is 12, and then we place them on a circle. We eliminate every 4th element, and those are the eliminated, and then we put them into groups, and we get rid of our dummies, and we have our partition balanced. Here's a different way to do it, but no dummy objects here. We have the same numbers as earlier, 9, 3, and 3, and we start by removing them, and then once we remove it, we don't count that position, and so on, and we have our 3 groups right there. So, let's talk about generalized run length encoding. So basically, we tried using that verse to create a sequence, basically four dotless, 5 dotted, and so on, and it's alternating between dotted and dotless letters. And we will use that to find exact cardinalities using Stirling numbers. So we have 3 cases for counting our GRL vectors. We have our very general case using Rn, so basically our partition level of vectors length n over R subsets, so we can have a group that has all objects and a group that has no objects. For our subjective case, where at least we need all R subsets to appear at least once, and the zero is our Stirling numbers, and we have our balanced case, where exactly S subsets appear Q plus 1 times, and the rest appear Q times, and N is QR plus S. Right. So after all these findings, we wanted to formalize our findings a little bit, so we moved on to thinking about formal language theory, which is a theory in computer science that basically resonated with us because we can create a regular language using this sequence, create a machine for it, and validate what we think we found. So our main problem is we needed to find a grammatical sentence. Grammatical not in the sense that we know it, but in the sense that makes sense in computer science theory. Whose concatenated letters match the alternative block pattern we had earlier. And over an alphabet partitioned into 2 groups, A and B here. So we needed a block language, which is the set of all letter string matching the block pattern. We needed a grammar, and we needed homomorphism. And then we asked ourselves, does this exist? So yeah, first of all, we found out that our language is regular. So basically, each block is a finite language, and regular languages are closed under concatenation. It's context-free, and context-free languages are closed under homomorphism, and they also closed under intersection with regular languages. And we found out that emptiness is decidable in linear time, and basically, our existence problem for that language is decidable in polynomial time, described right here. We also had a few algorithms. The preprint is on archive, but I'm so sorry I did not put it right here, but it's the name of the presentation. I'll put it back at the end. But we constructed an algorithm to check for its existence given a sequence. First of all, we constructed the DFA, which is the deterministic finite automata, and basically it uses states to go from oh my god, I'm so sorry. It uses transition states to replicate that sequence to create a machine that goes over it. I know this sounds not very professional, but I'm sorry, I went blank. And then we use that to build a word-level automaton for each word in the dictionary, and we needed to figure out which state transitions we need to succeed. We parsed over it, and we extracted our sentence. We also have another algorithm. It's also detailed in our paper, but it works, but in worst case, it's exponential, which is not very good. We also computer our complexity, and we can see that it's polynomial. So yeah, we were like, okay, this is cool. Those sentences make no sense. So with the computer science theory, let's think about an English adaptation. So we divided our alphabet into straight lined and curved, all in capital, because if it's not, it will be a whole different partition. And we were like, okay, we will use our verse to try and find a sentence in English that would make sense. We found these sentences. We will go a little bit into more details in a second. We also have multiple verses, not just that one, that give us multiple sequences following the same logic, just different step size. And here we go. So this is the first sequence, the first verse, and the first sentence. We can see that the sentence makes no sense. But we also had to add like an OH at the end to be to apply that sequence. We used the 2000 most used words in English dictionary, so that could be a limitation. But I mean, we're happy with that. It's something. Same for this one. We use step size 7 over 32 letters. Again, doesn't make sense. The Arabic verse does though. For whoever, yeah, the Arabic verse does make sense. And here is a different one with step size 5 and 30 letters. And these are our takeaways. So basically, we talked about our historical problem, partition algorithms, our general encodings, and we also have a Python code. We have a GitHub link, and I think it's mentioned in the paper for anyone who